So welcome to this evening's webinar. It's a pleasure to have with us Ajay Soni from QTF campus in IIT. So Ajay is a PhD from the University Consortium in Ahmedabad, many years in Virginia. And after his PhD, he moved to Singapore for 2 postdoctoral stints at NTU and MS. So this was 2014 to 17? 9 to 13. And after which he has been a faculty at IIT Mandi, amongst the earliest, I guess, the Kanas Metaphysics community there. And there he has a very active research group working on Raman scattering, thermoelectrics, 2D materials, and so on. He does a lot of work on thermoelectrics, but today, partly due to my prompting, his talk is not on thermoelectrics but on charge density waves in 2D materials. So we look forward to the talk.
Okay, so at the outset, let me first thank Sunilda for accepting that I can visit here and giving me chance to interact with a lot of friends. And of course, meeting Professor Ramki was a cherry on the top, I would say, and interacting with the students. So, what I'm going to talk today is a different perspective of one of the interesting phenomena in condensed matter physics. When we talk about solids or condensed matter physics, we talk about either atoms or the moving charge or the electrons, we say it. Okay, and the other perspective is actually you have atoms surrounded by the electron cloud, and now that cloud can move around as well. Okay, but when you talk about charge density wave, it has a lot of interesting signs, and I put a new word here, which is supermodes. Okay, this is I'm coining it because some of the new modes which we have seen in Raman modes coming because of the charge density wave in those materials. Okay, and they are only associated with the charge density wave. Then I use the word symmetry breaking because what we are going to do is I am going to talk about if you reduce the dimensionality of the chalcogenide material, you will have new modes which are coming up, and you will see that there are new phenomena which is coming up based on the temperature dependent studies. Okay. So, I am from IIT Mandi, and these are the two campuses. So, primarily the PTech or the teaching activities are here. This campus was built up before, and most of the research activities are here. So, we have a this is the class 100 clean room facility, almost like 10,000 meters, and we have advanced material research center where most of the material science related activity or the facilities are there. So, my office is here, my teaching is here, and my house is here. So, I have to travel every day there. Yeah, all right. Okay. So, this is the outline of my talk. I will give you the overview of the research activity, what we are doing with a few slides. Then I will move on to the actual objective of the day today. So, I am going to talk about some tutorial slides for the students where what is the charge density wave and how it is important or why it is interesting. Then I will talk about what you can see using Raman spectroscopy for charge density wave. I will give you what are the examples or what are the evidences of the charge density of collective modes, because there is something happening in the material and which is giving rise to the new modes in 3 different materials. What is the effect of the dimensionality on one of the example, and I will tell you why we chose 2H tantalum sulfide as well. So, in my group we primarily focus on charge transport in materials. So, we work on thermoelectric materials, we work on quantum materials like bismuth telluride, bismuth germanium telluride. We work on the topological insulators like tin telluride. We also work on a lot of complex structures to get the thermoelectricity, and these materials are important not only for the fundamental understanding, but for the technological application as well. We also work on some of the carbon based materials and the flexible thermoelectric devices. So, kind of like a functional materials which we have built up in the lab there. Recently, we started looking at the multi-body phenomena using light matter interactions in 2D materials, or one can say the layered materials which are the hot cake these days, like MOS2, bismuth selenide, and some of the other chalcogenides. We also do, it seems like when I visited all the labs, they said every lab had some developmental work. So, we also do some sort of instrumentation for the customized measurement, and these are the publications from my group in last 12 years, and our research is generously funded by the various funding agencies. So, I am thankful to them. This is my group almost like 6 months ago. Some of the students, they moved out. All right. So, what I am going to talk today is the metal chalcogenides, because these are the good CDW material. When you talk about CDW material, there are a lot of materials which shows the CDW, like Hegame lattice, like the cuprates as well, and some of the superconductors also show the charge density wave. But since these materials are easy to prepare in the lab, and it is easy to probe them using the light matter interactions. So, these are metal chalcogenides. So, chalcogenides are here. I am going to use only these 3 elements here, because they belong to the same column here, and we have done some work on the rare earth tritelluride as well, but for that perhaps I will come back and give another talk on that. Okay. So, let me tell you what is charge density wave is. So, in solids, you know that there are specific atomic arrangements, okay, and there was a need for the condensed matter physicists to understand what is the origin of superconductivity. There is the interaction of the electrons with the phonons, okay, and Peirce was trying to understand it with the one dimension chain of the atoms. He was not able to explain it in a clear way, but he opened up another area of charge density wave. So, what you have here is that, you know, the atoms are connected by the spring, which is a textbook definition that, okay, you wanted to understand the phonons. So, you have a single kind of atoms that are connected by the spring, and if you look at the band structure here, so this is your Brillouin zone boundary. So, this is your Brillouin zone, and now the charge density is unperturbed charge density is given by this one. But with the thermal fluctuations, you might see that these atoms, when they are vibrating, you may have some of the superlative structures which has a periodicity which is other than this one, and the charge density wave is driven by, like, given by this particular formula. So, you have a modulation of the electronic charge, and you have a modulation of the lattice as well. So, now let us consider that this is A, and now this is 2A. So, when you look at the reciprocal lattice space, so it is 1 by A and 1 by 2A. So, your Brillouin zone is half here, okay. So, you have a folded Brillouin zone, and you have a gap which is coming up because of the periodicity here, and that gap is the charge density wave gap. Okay. So, your charge density wave is given by the amplitude here, and you have the wave vector and the phase vector, and they all are actually giving rise to how the modulation will look like for the charge density. What are the possible origins of the charge density wave? Okay. In literature, if you look at here, one of the possibility is the Fermi surface nesting. So, in one dimension, you consider this red one is the 2 Fermi surfaces of the 2 atoms here, and they are connected by the wave vector here, and these are the connecting vectors. So, one dimension charge density wave. In 2 dimension and higher dimension, it is more complicated because the q vector does not lie in the Brillouin zone. Okay. So, Fermi surface nesting is one, and this particular part also gives rise to the instability in the electronic susceptibility. So, this is Frolic function here, and the Lennard function, it shows that, okay, 1 dimension, 2 dimension, 3 dimension. So, the charge density wave is very complicated here, and now the important aspect is the q vector here. I will tell you what is this q vector is. So, if you look at, so these are the pictures which tells that, okay, these are the electronic instabilities which are giving rise to the instabilities in the lattice. And now, if you look at, if your material is at higher temperature than the charge density wave temperature, you have a phonon dispersion, which is usual acoustic phonon, you can see it here. But when you go below, very close to the charge density wave temperature, or maybe equal to that, you have a anomaly which is coming up in the phonon dispersion curve. So, you have the lattice instabilities which are coming up, okay. And now, how do you compensate these instabilities? So, you have the electron phonon interactions where the electronic instabilities drives the phonon instabilities, and you have the involvement of the electron phonon coupling. Okay. So, you have Fermi surface nesting as one of the origin, you have the lattice instabilities which describes the charge density wave, and you have electron phonon interactions which can be the reason for the charge density wave as well. So, these are one of the way, okay, you can represent the lattice instabilities. Okay. Let me tell you how do you classify the charge density wave. So, you can classify charge density wave in commensurate and incommensurate based on the periodicity of the undistorted lattice. So, let us say This is undistorted lattice with the periodicity of A. If the new lattice which is reconstructed because of the charge density wave does not have a periodicity in the integer multiple of A, you say it is an incommensurate charge density wave. If the periodicity of the newly constructed lattice follows the integer multiple of this A, then you say it is a commensurate charge density wave, and this is how you can classify different charge density wave materials. Some of the material shows both kind of charge density. So, these are more the lattice instabilities which shows the incommensurate charge density wave. All right. Now, when I am saying that there is a folding of the Brillouin zone, okay, so you are breaking the symmetry, you may expect some of the new phonons which are coming up. So, for example, you think about it, this is the primitive cell for the undistorted lattice, okay, represented by A1 and A2. Now, this is new one. So, now you see the Brillouin zone which was like this one, which is half of that, okay, and right at the boundaries you will have the gap, and if you look at the phonon, this is the original lattice and this is the charge density wave. So, you have new modes which are coming up, and these modes are called the zone folded mode because it is coming because of the folding of the Brillouin zone. Okay. So, you have the collective amplitude modes, phase modes and the folded modes. These are the modes I am saying, these are the super modes, okay. But how do we observe them, that I will take it, okay. Now, the discussion is that whether the Fermi surface nesting is the reason for the charge density wave or it is the electron phonon coupling which is the reason for the charge density wave. So, different materials will show a different origin for the charge density wave. For example, if you have a metallic system, so you say that it is more the pulse distortion or the reconstruction of the lattice, but most of the chalcogenide materials are showing the charge density wave is driven by the electron phonon interactions, okay. Now, what are the evidences of the charge density wave? Suppose you have a material, okay, and how do you see there is a charge density wave? So, what you do is, because I am talking about electronic instabilities and how do you detect them? You do the transport measurement and you see that there is an anomaly or there is a deviation from the usual behaviors, okay. So, this is resistivity as a function of temperature. If you look at here, this is 1T tantalum sulfide. So, you have a first order phase transition like, but there is a charge density wave here. You have 1T tantalum selenide, there is a jump and then this is the behavior. So, these are actually the signature of the charge density wave. Okay, now, there are other ways also to explain this one. Okay, you have metal insulated transition, you have structural phase transitions and all those are involved. Okay, but these are the materials which shows the charge density wave. The another evidence what you can see is that you go to the charge density wave state and do the transmission electron microscopy or you do the electron selected area electron diffraction. You will see that on top of the usual structures, you will see some of the signature of a new structure, you call it as a superlattice structures, which shows that this is the CDW state. And now, so since the electrons are involved, phonons are involved, so there is a way that, okay, you do Raman spectroscopy, you will get the signature of charge density wave as well. So, we do a lot of Raman spectroscopy to see the charge density wave. Okay, this is just one line here that, okay, when you do the light matter interactions, a lot of insightful information you get it from the material, not only the elastic scattering, the inelastic scattering which is Raman scattering is important, okay, and you get a lot of information. And primarily we look at these are the quantum interactions in the material which are probed by the Raman spectroscopy, that is what we are focusing these days. And of course, when you do the Raman spectroscopy, so you have an incident light and you have a Rayleigh light which is without change in energy, but at the same time you also have certain amount of radiations which are coming up which has energy other than the incident light, and these are the Raman intensity, we call it as a Stokes and anti-Stokes lines. Alright, and let me just give you, I just wanted to, I do not want to discuss much on the other characterization because my focus is on the Raman, but as I mentioned that, okay, tantalum sulfide, niobium selenide and VAC2, these are the materials which shows charge density wave and they are unique, so I club them together. Now, we will talk about that what is the resistance, okay, resistance versus as a function of temperature. So, for the tantalum sulfide right at 76 Kelvin, it shows incommensurate charge density wave. Now, we look at the niobium selenide, it shows charge density wave at 30 Kelvin and a superconductivity at around 9 Kelvin or something, 7 Kelvin, sorry. And you have VAC2 which shows both kind of charge density wave here, the incommensurate charge density wave and commensurate charge density wave, which is visible here in the transport data, and this is the differential resistance here. Now, you see it has a higher temperature, this is also at higher temperature because there is a competition between superconductivity and charge density wave, that is what the charge density wave transition is lower for the niobium selenide. Alright. these all are bulk. And so we started actually in 2019 with one of the PhD students. She was working on 1T VSE2, and so if you look at the transition metal dye chalcogenides, if you do the Raman spectra, you usually get the A mode and E mode. A mode represents the out of plane vibrations, E mode represents the in plane vibrations of the atoms. For example, this is the AG mode. So the vibration of the sulfur and sulfur atoms are, or chalcogen atom is out of plane, and here it is the in plane mode. Room temperature, no charge density wave. You have A1G mode, you have EG mode. Okay, I am not going to talk about this one at this moment. After 4 slides, I will talk about it. You go to 10K. 10K is commensurate charge density wave. What is happening here? So you have 2 new modes are coming up, right? And I will not go into the detail because this is well studied system now. 100 Kelvin, the charge density wave transition for the VSE2 is around 105 or something. So if you go below 100 Kelvin, there is nothing here, but if you go down until 40 Kelvin, you have something happening here which goes up. So you have these modes which are coming up only in the charge density wave. You have certain modes which are coming up in the commensurate charge density wave state. So there are 2 new modes coming up. One is coming because of the incommensurate region, and another one is coming because of the another ordering here. And so the intensity of the EG mode rises very significantly. And so this is okay. This is just the temperature dependence. So these usual softening of the phonons here. But what is important here is the integrated intensity of the Raman mode specific to the EG mode. You go from here to here, which is like 120 Kelvin to almost like 40 Kelvin. You have instabilities in the structure which is shown in the integrated intensity. And when you go further down, so you again have a hardening when you go to the low temperature. Okay, so this is represent there is new kind of ordering which is coming up. Okay, so here what we wanted to convey is that these kind of instabilities are coming because there is an involvement of the electron phonon coupling, and now it is not the Fermi surface nesting, it is the electron phonon coupling is more important in these materials. This is the message I wanted to give with VSE2. All right, we looked at the spectra of other materials, okay, and to our surprise there is something which is coming up in every charge density wave material, and we call it as a 2 phonon mode. I will tell you why we call it as a 2 phonon mode, but if you do the Raman, you get EG mode here, AG mode. So this EG mode represents the in plane and AG mode represents the out of plane. Then you have a mode which is coming up here, and let me just give one line here that okay, between the niobium selenide and tantalum selenide, here in niobium selenide the selenium bands overlap with the niobium bands, okay, even crosses the Fermi level. So you have a pocket in case of niobium selenide, that is what the superconductivity is there, but this is not there in the tantalum sulfide. Here it is clean yours because the phonon dispersion here, so it is clean and you do not have an instability here, but if you look at here the Q1 and Q2, there are 2 vectors. So one is from gamma to K and another one is gamma to M. So you have 2 new vectors, okay, and there is an instability here because the frequency is negative here, okay. So the instabilities in tantalum sulfide can be at higher temperature as well. All right. So this is the tantalum sulfide. There is a Fermi surface, like there are vectors which are related to the Fermi surface nesting here, but there are involvement of the electron phonon coupling as well. All right, so because these niobium selenide or tantalum sulfide have 3 atoms per primitive cell, so you expect like 9 vibrational modes, out of which 3 will be the acoustic and 6 will be optical, but not everybody will be seen in Raman spectra. The interesting aspect here is if you look at the phonon density of states, you have frequency versus PDOS. This is tantalum sulfide. So until 140 you have the modes which are primarily because of the vibration of the tantalum atom, because it is heavier, so you will have low frequency vibrations are dominated by the tantalum. The high frequency will be dominated by the sulfur, and there is a gap here in the phonon density. So which means you do not expect anything in that region, but this is the region of 140 to around 180 for tantalum sulfide, 140 to around 180 or 200. That is where the 2-phonon mode is coming, okay. From where that mode is coming, okay. What is the origin of this mode, okay, and what is the symmetry of this mode above all actually, okay. So, theory does not say there is a mode, this is there in the niobium selenide as well, but I have not shown it here. So, now what is happening is, if you look at the textbook definition of charge density wave, it is associated with the Cohen anomaly, and what is Cohen anomaly is that right at the q vector where you have the charge density wave gap, this is usual phonon dispersion for the acoustic mode. Right at here you have an anomaly, okay. There is a dip in the phonon dispersion, and that dispersion is the Cohen anomaly now, and the energy of this Cohen anomaly is half of the 2pH mode. So, 2pH mode has the energy which is double of the Cohen anomaly. Now, what happens is, this is associated with the acoustic mode, but when you talk about the observation in Raman spectra, you talk about the optical mode, alright. So, what is happening here is that you have a incident wave and you have a scattered wave, it is interacting with the lattice. So, you have electron phonon coupling, okay. That electron phonon coupling actually stabilizes or conserves the total energy in this instabilities as well. This 2pH mode has the energy which is twice of the Cohen anomaly. What is the symmetry of that? So, what you suppose you wanted to find out the symmetry of the mode, what you do is you do the polarized Raman spectra. So, you do xx polarization and xy polarization. If both the modes are there in xy as well as xx polarization, you call them as a EG mode, because they are symmetric, okay. But if one of them is in xx and is not there in xy, these are the AG mode. Now, if you look at here this 2pH mode, there is a slight change in the intensity of the mode at the xy geometry. Now, whether I excite with 532, whether I excite with 633 or excite with 785, I see this signature in all these Raman spectra. So, which means this particular mode has a symmetry which has both the symmetry, I would say, or it involves the vibration of the atoms in both the directions, alright. How does it look like? In general, when you talk about AG mode, you only talk about the vibrations in this direction. When you talk about EG mode, you talk about this direction. So, you have the vibrations which are involving both kind of symmetries here. So, now symmetry wise it is okay that you have both kind of symmetry it is. So, the polarized Raman spectra indicate that 2pH mode has predominantly longitudinal vibration and plays an important role in the CDW superlattice or CDW instabilities, because that is visible in everything. So, now if you look at the temperature dependent Raman spectra, there is a shift of the 2pH mode in both the cases. Yes, okay. So, you ask the question, how do you know that it's electron phonon coupling. So, normally when a solid you heat it up, okay. So, there is a thermal expansion, there are thermal processes, okay, and there is an enharmonic term which is involved, okay. Now, if you fit the frequency versus temperature with the enharmonic model given by this equation, if it is following that, okay, that means there is no involvement of any extra process in that. But if there is electron phonon interactions which can drive the enharmonicity or other factor in that, so which is observed at low temperature, which is in case of tantalum sulphide it is below 100 Kelvin, you have a deviation. Now, the deviation actually tells you that there is an involvement of electron phonon coupling. So, that is the signature, and for NBSE2 because it is at very low temperature, alright. So, you have an involvement of the electron phonon coupling. So, the charge density wave in this material is driven by the electron phonon coupling, okay. Most important here is that, come on move, yeah. If you look at the deviation, the EG modes involve too much of deviation from the enharmonic mode. So, these in plane modes are more sensitive towards the charge density wave superlattice formation, because the charge density wave is perpendicular to that, yeah. It is a one dimension charge density wave there, yeah. Alright. We also estimated, so if we look at the temperature dependence of the 2pH mode, okay, from higher temperature you go down and it goes up again, okay. So, this is if I go from low temperature to high temperature, we call it as a softening. From here to here, if I go with the temperature, I call it as hardening. all right, and this is there in both, and by fitting these equation with this equation we can estimate how much is the anharmonicity in the sample, and at the same time how much is the electron phonon coupling constant in these materials. Okay. So, if you look at here the delta value which represents the enharmonic term, I think it is lambda is here. Okay. So, this is here, you see the niobium selenide has is more enharmonic, while the electron phonon coupling is higher in tantalum sulphide. Okay. And now we wanted to probe more into the electron phonon coupling, because that is the signature we get it. Okay. That is what we chose tantalum sulphide over niobium selenide to exfoliate it and see what is the effect of dimensionality. Okay. And as I mentioned that there are charge density wave supermodes which are coming because of the folding of the Brillouin zone, and then these are the modes, we call them as a collective modes, well reported in literature that these are called the collective modes which are seen in the Raman spectra. Yeah. So, with 532 we have seen 3, because some of the lasers will not excite some of the modes. So, you have these modes, we call them as the amplitude mode or the phase mode, and these are the super modes representing the charge density wave. Alright, I will switch my gear and
sorry for interrupting.
yes.
Why is only some wavelengths excite some modes and not the other?
It is just the energy actually, energy of the vibrations as well as the excitation energy. Some of the vibrations will not be excited with certain energies. Yeah.
That's interesting. Maybe it's a photon, and in the end it has to interact with the lattice and.
It's not that straightforward. You need to have like you need to have like an integer multiple of the photon versus this energy. Yes. Okay, and since I am talking about modulation of the lattice, I am talking about there is a formation of lattice superlattice structure. So, one thing is that my structure may not change, but the symmetry will change, all right. And when you talk about changing the dimensionality, you expect that at least the translational symmetry will be broken, yes, and then you stop yourself, okay, because that is very obvious. So, when I am talking about dimensionality effects, so what we have done, we have taken the tantalum sulphide and exfoliated using the Scotch tape, and we have moved down to single unit cell which is 3 nanometer. So, almost like 2 monolayers and a van der Waals gap. So, single unit cell. Going beyond that was not possible for us, and there are more reasons actually we have not done anything in the monolayer. But now in the literature if you look at there is a debate. People say that monolayer tantalum sulphide should not show charge density wave. Some people say that okay, there is a charge density wave signature in monolayer as well. What is the, I mean, like they do with the different experiments, I mean, like different techniques, and try to show that okay, there are some patches where you will see the charge density wave. Okay. Now this paper says as the film thickness decreases, the charge density wave, commensurate charge density wave phase transition temperature decreases and vanishes at the critical thickness of 3 nanometer as presented in figure 4e or something, okay, all right. And we try to see that. So there is a debate actually in monolayer whether the charge density wave is there or not, all right. So they have done I mean like different kind of measurement, somebody has done with the TEM on the monolayer or something, yeah. But it is not clear, mostly the non-linear optical measurements also people have tried to see that, yeah. So now I am talking about when I am going from bulk to monolayer, what exactly it is happening. Number 1, I am actually slowly taking out the top layer from there, okay. So number 1, my restoring force in the outer plane vibrations is less, okay. Second, because in the bulk you have a translation symmetry, I mean like if you see it here, it remains the same, okay. But if I go to the monolayer regime, to bilayer to monolayer, what happens is that if I have a trilayer, I have a non-centrosymmetric structure. If I have a bilayer, which is the case of a unit cell, I have a centrosymmetric structure. If I go to the monolayer, this is a non-centrosymmetric structure. So symmetry is changing with the number of layers you are either removing or putting it up, either way you can think about it, all right. Then we did some calculation, we talked to some of our collaborators, okay. So this is phonon dispersion, frequency versus momentum here. The bulk has an instability only at low temperature, And how we are changing the temperature in the calculation? We are changing the smearing factor. That smearing factor will not tell you the absolute temperature, but it will tell you what is the range of the temperature where the instabilities can exist. Okay. So, I am changing my smearing factor from 0.01 to 0.3 here. So, this is bulk, this is bilayer, this is monolayer, but you will not be able to see any or conclude from this, but you will be able to conclude here. This shows that almost like 200 Kelvin temperature. This is my monolayer, this is my bilayer, and this is bulk. So, bulk does not have any negative frequency, no instabilities at higher temperature like 200 Kelvin, but bilayer or monolayer can have this charge density with instabilities even up to 200 degrees centigrade, 200 Kelvin. Let us see the Raman, how it looks like. Okay. So, this is 300 Kelvin, this is bulk, very usual Raman spectra what we have seen in the previous story of the 2 pH mode, 10 nanometer, 7 nanometer, 3 nanometer. Now, in 3 nanometer we have a contribution which is coming from the substrate because it is an extremely thin layer. Now, if I go beyond 3 nanometer I will have substrate contribution higher, I will not be able to resolve or fit my Raman data. So, that is my limitation. So, we stick to the 3 nanometer and it is centrosymmetric bilayer system and it is a unit cell, alright. At room temperature, none of these are showing any kind of signature of charge density wave. At 10 Kelvin, this is the bulk, you have seen that 2 pH mode is there is a very feeble mode here, 14 nanometer, 7 nanometer, and you have some modes which are coming up here, but you have a mode which is called M1, M2, look at the vertical axis here, this is 2 pH mode, and you have M1 and M2, and there is another M3 mode here which is coming up here, and this is usual AG mode. We have done the polarization, try to find out what are the symmetries of these modes. Okay, we found out that these new modes have a different symmetry. Okay, so we have a mode which is at 125 centimeter inverse, we have another mode which is at 158 centimeter inverse, and the third is 334 centimeter inverse. We identified that this is E mode, this is A mode, this is E mode from the polarization. Okay. And another important aspect is that these modes are available only you go below 16 nanometer. Yes.
I was curious why the signal to noise ratio goes bad when you go towards thicker plates. Do we understand this?
Okay. So, when you talk about the thicker sample which are crystalline, you have more scattering processes coming up there. The cross section is less than the for the monolayer or something. For example, in graphene, the cross section is extremely high. So, you get a extremely beautiful data for the G mode and D mode. Okay. But if you take the graphite, it's not, the noise ratio is larger there because the cross section in the monolayer is high for the graphene. Okay. So, this is bulk and this is 10 Kelvin here. Okay, this is the temperature scale. So, 300 Kelvin, this is 10 Kelvin, 27 nanometer, 16 nanometer, 10 nanometer, 7 nanometer and 3 nanometer. So, I have new modes which are coming up below 16 nanometer, not existing at higher thicknesses. So, now you have charge density wave modes and you have a modes which are coming up because of the dimensionality effect here. And the higher thickness does not have anything above 16 nanometer. We have in between as well, but we have not shown the data here. So, anything above 16 nanometer, you do not have these new modes which are coming because of the dimensionality, and we try to understand the fitting of the M2 mode, okay, which is very interesting. And this is the Raman mode for the one of the mode which is almost like 158 or something. We fitted with the Fano line shape analysis, and we found that the Fano line shape actually tells you how much is the involvement of the electron phonon coupling, and the slope of the Fano line can tell you whether it is N type or P type material as well. Okay. So, we found out that there is a clear cut involvement of the electron phonon coupling below 16 nanometer or 10 nanometer, which is enhanced when you go to the dimensional, which is enhanced in the lower thickness flakes. All right. Then we also identified from the deviation from the anharmonic behavior that if the deviation is there, then you have more involvement of the electron phonon coupling in these materials. I will not go into the details of all those here, because they all are giving the same message that you have a large electron phonon coupling which is involved specific to the tantalum sulphide, and that is what the, as I mentioned, that we chose because we wanted to see how much the electron phonon coupling. Okay. So, let me conclude it here. So, this is 16 nanometer, this is 10 nanometer, this is 7 nanometer, this is 5 nanometer, this is 3 nanometer. Okay. So, now we have a typical charge density wave region, incommensurate charge density wave region, which I have shown you in the VSE2 also. It is going down, so you have a different kind of ordering there. We have the softening which is going even at higher temperatures. Here you can think about it, it is like 150, so 160, 170, nearly 180. I am going down in the thickness, I am going up in my temperatures. This is TICDW, so incommensurate charge density wave, 5 nanometer, 3 nanometer, and this is the thickness versus transition temperature. So, charge density wave instabilities at lower thickness can exist at higher temperature. So, very interesting actually. Okay. And these are the signature of the charge density wave materials. With that, let me just conclude. Okay. So, I talked about the charge density wave, maybe it is a tutorial for some of the expert, but I talked about how you can get the charge density wave modes, the origin and symmetry of the 2 pH mode. We are still in a process to understand this 2 pH mode in a more detail, and maybe within few months or something we will clarify it, what exactly it is happening there. 2 pH mode, the one which I have not mentioned, I have not shown the data, but let me just declare it here. It is the interaction of 2 acoustic modes with the opposite momentum, okay, because with the wave vector around 2 kF, okay, and they are giving rise to a optical mode. So, 2 acoustic mode giving rise to 1 optical mode is one of the conclusion we wanted to draw from there. And so, that is, and of course, the confinement effect and the breaking of the symmetry at nanoscale gives rise to the higher TICDW, and we have observed some new CDW modes because of the dimensionality, and this TICDW has an inverse relation with the thickness of the flake. With that, I thank the funding agencies, the group members, and of course, the collaborators. Chandan has helped us a lot in the thickness dependent work. Umeshda is helping in 2 pH mode, and of course, the other people are involved in other research. If you have any questions, I will be happy to answer. Yes.
So you are telling that in bulk you have this 2 phonon mode, I mean 2 pH mode, which is there already. In addition to that, you get sharper modes in thin flakes.
Yes. So, if I go down in thickness, okay.
You get those sharper modes.
Mm.
The origin is still electron phonon, or it could be Fermi surface.
Now this is pretty clear that these materials have electron phonon coupling driving the charge density wave, not the Fermi surface netting.
Even the new modes, which are pretty sharp.
So, new modes actually are coming up because of I mean like the new super lattices which are coming up, because we are breaking the symmetry there actually. So, these are coming because of the symmetry breaking there. Yeah. But these modes does not tell that okay, there is a Fermi surface nesting involved here.
Yeah, I was just wondering, because this measurement will not take care of whether electron correlations will affect the broadness and sharpness. That is why I was asking.
No, because these are phonon modes, so it is more or kind of like how much they are populated with temperature. That is the intensity actually tells you how much phonon modes are populated.
Yeah, but electron phonon coupling will contain.
Yes, sir.
I have a few questions and few suggestions. So the first one is that it's interesting that the electron phonon coupling is increasing when you're going below 16 nanometers. Is there any understanding why 16 is so holy, or is it something which happens?
We have not done the thickness dependent calculation. That would give us some idea, but this is just the experimental observation, and we just try to understand what is happening with the temperature. Yeah.
Because there are some calculations, I don't remember now, 3 years ago, the band structure calculations suggest that there is an enhancement of electron-phonon interaction in thin films. Okay, so possibly I think your measurement seems to support that view.
Yes.
Because a priori it's very difficult to think that why is it happening only in thin films. See, generally it is known in aluminium, you know, the aluminium, the TC goes up because it becomes a thin film because there is a lattice softening. So it's not clear whether there is an extra lattice softening happens when you go to the thin film range. This is one thing which we need to first find out. The second thing is the CDW increasing with the thickness is one aspect. You can take over the counter question that if you look at titanium ditelluride, I don't know whether you're familiar with this material. This is TiT2 formed the same trigonal structure. This is the only example which I know that it doesn't, bulk doesn't show CDW.
Its monolayer shows.
The monolayer is showing. Okay, there are here very good measurements which shows that it is a CDW. Maybe your technique could pick up that, you know, go to the monolayer and see whether these phonon modes which are there, which is enhancing your CDW, may be responsible for bringing out the CDW, because that is an unanswered question in the last maybe a decade or so. So I think titanium ditelluride is probably a smoking gun proof for your technique to show that it is really these modes which are bringing out the CDW in this.
Yes.
And so is niobium disulfide. See, there are some measurements which shows that there is a local CDW traces in these materials. But people have not, see, niobium disulfide also doesn't show CDW. But the thin films have this effect there. So the mystery is that your experiments seems to suggest that there is an enhanced electron-phonon interaction. That is good, but we need to fix why it's happening at certain limit and why it doesn't happen. But also a smoking can prove that the CDW is induced because of this in titanium.
Yeah. Okay.
That's all I want.
Yeah. Thank you, sir. Yeah.
Nice talk.
Yeah. Thank you very much, sir. So let me come back to the all 3 points. Number one was what is happening below 16 nanometer. Okay. So one of the reason which I feel personally is that because I am reducing the weight on the thin flakes, 16, 10. So actually the restoring force of the vibrations is decreasing. At the same time, because whatsoever the phonons I am talking about, they are confined in 2 dimension. So there are 2 factors. Okay. The EG mode mostly tells about the phonon lifetime as well. Okay. If it is increasing, that means there is a confinement effect. So, but I am not sure at this moment whether this argument will really go for that. Yeah. Second thing, on the tantalum telluride, we are looking for some good crystal. Just half a micron is good enough for us. That's a problem because we tried in lab, it's difficult to grow. And monolayer is even more challenging because exfoliating and then the substrate effect will dominate. So these are the 2 reasons we are not able to show, otherwise we had this in mind that this is one of the good example to show. Yeah. Thank you for your suggestion, sir. Yeah.
So my question is more at the student level. So if there is a doubling of the lattice, you know, which happens at the charge density transition, and there is no lowering of the symmetry. The global symmetry is still the same, just the lattice parameters double. So how will that affect the Raman spectrum?
Okay, so zone folded modes are one of those examples where you will have a new modes.
So will you have some new modes? So will that not confuse with, you know, I mean, what I mean to say is that sometimes you get new modes because there is a change in structure. Sometimes you get new modes because there is a doubling of the lattice parameter, but there is no change in the global symmetry. So how can one, you know, distinguish these 2 scenarios?
Okay. Okay. First thing I wanted to clarify that don't get confused with that. Okay, it's just the doubling of the lattice parameter. It can be in between. The doubling of the parameter is just a simple model to explain charge density wave. Yeah.
Case, very special case, is doubling.
Yeah.
You can have irrational numbers, or you can even have, you know.
That's the incommensurate charge density wave. Okay. And most of these materials have the incommensurate charge density wave.
Right.
Okay. Very limited number of materials they show the commensurate charge density wave, and they will be more interesting to see using the transmission electron microscopy at low temperature. So of course, Raman, we will be able to get new modes, and not only that, actually the moment you change the symmetry, like the center of inversion symmetry, you change it, you get new modes, which we have seen it in tin telluride, which I have not shown it here. So, what we have done, tin telluride is a cubic system, you do not expect Raman spectra from it, because it is symmetric. Okay. We put Mn into it. So, the moment you put Mn into it, because the different ionic size, so Mn is replacing Sn. So, now you are changing the center of inversion, and at low wave number, I wish I could show the data, we have found a new modes, okay, which are coming because of the breaking of the symmetry there. So, the symmetry breaking will give you new modes if the material has those modes actually. Raman can detect it.
And my second question is related to the electron phonon coupling, which leads to hardening of the modes, right? That you showed, modeled it with lambda times t. So what would be the corresponding signature of electron Fermi surface nesting in the Raman? Electron phonon you can pick by hardening of the modes, right? But how would one know that there is a nesting and which is leading to this?
Okay. So, Fermi surface nesting, I do not know at this moment that will Raman.
So, I don't think Raman can
Pick this.
So, when you talk about the electronic instabilities, you
people are saying why, see there are three ways the CDW can happen. One is the one which is piles, second is this electron phonon, right? There is charge order.
electron correlation.
So, the only way to check there is a nesting or not, looking at this crystal structure, usually 3D it is very difficult to find. Then you do an RPS or D as one or whatever. So this one, so you have that information before you do the Raman.
But it would be interesting to do Raman on a system which is known to be, CDW
Correct.
because of nesting, and see what kind of changes it will.
These are metallic system, that is one of the problem for metallic system will not give you good Raman signal.
Like in iron arsenides, there is a strong Fermi surface nesting and there is a spin density there.
I am looking for some of the system where.
See, the problem is that many of these real nesting, then it goes to an insulating state. So he can't find this 2p mode out there, like this blue bronze, this and so on. He needs some conduction, but not to be the metal. But iron arsenic said it's a good system to work on.
My question again is at the level of students. So these charge density waves, they are static as a function of time or they propagate? Can one write a real?
Sir, please help me.
No. See, you can if it is incommensurate charge density wave, you can slide it. So you can you put a electric voltage and you can see the movement in time. But if it is incommensurate, they are pinned. It's like a standing wave kind of stuff there. But incommensurate, you can put a small blue bronze, or standard tantalum diselenide. You can put a voltage and you can see the movement sliding of the CDW.
STM is one of the experiment one should do, and I am not able to find a good STM guy who can do STM on these samples at very low temperature. Okay. Otherwise, I would not have been struggling with the editors for PRL. It is going in PRV.
Short question. So, can one also learn something from the shear modes in Raman spectra for the charge density wave? Shear modes as in which appear at very low frequencies.
Not specific to the charge density wave, but shear modes you should be able to see in Raman. We have some examples. In case of some of the samples which Kanishka had shared, the perovskites, we have seen that, and we were able to see some of the rotational modes as well. Okay, and these are good crystals actually. Okay, so those I think it was published in Chemistry of Materials or somewhere actually. But we just
I'm asking.
wait. The only thing is that mode should polarize the sample.
I was asking because normally shear modes they shift drastically with thickness, with sample thickness. So maybe one can.
Okay, now I got it. What you are asking? You are asking about thickness dependence. So, for example, monolayer MOS2 doesn't have that mode, and bilayer will. Okay. Okay. We have not seen it. I wish MOS2 shows charge density wave. So we have seen those modes in Raman for sure. because you need cross section for the for Raman at that particular frequency. Yeah. I mean, in these samples it is not. MOS2, if it is there, we are able to see those interlayer breathing mode. Yes.
So just for my understanding, so take the finally with the Fano symmetry, you got the proof for electron phonon coupling, which you have figured. Before that, earlier you used the equation for the anharmonicity and then electron phonon coupling. So what extra information you got earlier?
Okay, so that was the overall sample. You have all the modes. You do the temperature dependent. Deviation will tell you there is an electron phonon coupling. Okay, here this is a new mode which is coming because of the dimensionality. That's an M2 is a new mode. We wanted to find out what that mode is.
But earlier you did not have the Fano symmetry signature.
We are not. Yeah, we are not. Yeah.
New mode you have.
Yes. Yes. Yeah.
But this Fano coupling, does it show a systematic increase as you decrease the number of layers? In this field parameter?
Let me just check before I answer if I should not answer wrong. Minus 3.85, 466, 3 number 7. It's non-linear.
So like just
Again, it is because of the centrosymmetry and non-centrosymmetry, because 7 is odd number and this is even number.
It will depend on the number of layers.
Yeah.
just to like for my understanding again, just to conclude. So even if you do not have this Fano symmetry signatures, fitting with that equation, you can point out there's a signature of electron phonon coupling.
Okay.
And then if you have it, then it's again ultimate proof you can.
So now here there are two parameters. In earlier case, I don't know what is the shape is. I just know this point as a function of temperature. All right. It's a temperature dependent behavior. All right. Here, I don't know what is temperature. I just know that what is the shape of this Raman peak. Okay. So this is a shape analysis from the Raman. That was just the frequency dependent, temperature dependence of the frequency.
I think his question is that if you take the same peak for this spectrum and then you plot the position of that peak with temperature, then you should see the hardening, right? I mean that will be an.
Let me check whether I have that or not. Because we have not done it for all those, but we are talking about M2. Yes, here it is there. So this is M2 mode, and this the pink color is M2. 10 nanometer it is there. 7 nanometer. 3 nanometer it is almost like stable. Okay, and this is line width. Of course, the line width is totally because of the substrate contribution. Actually, this line width is not good. Actually, you can't conclude from here. But certainly, the behavior of this one, you can see that 160 to 158, 164, 164, it's stable, and we have like resolution of 1 centimeter inverse or something, 0.5 actually.
The question is, if instead of M1, M2, you take some other mode and do the temperature dependence of that mode, will it show hardening? I mean, there are many other modes. Right?
Yeah, so I have shown actually, yes, hardening.
Like for any of these other modes, it is. But anyways, I mean, this is.
I think I have shown in the bulk material. Yeah, it is there. Yeah.
So one was just again in slide 32. So the polarization dependent variable. So that is for the sample.
I think its polarization dependent is for the. This is here. Sorry, I missed to mention actually which sample is this one. But if I look at here, it has M2 mode, M3 mode, so it must be a thin layer, and it is not 3 nanometer that I know.
And what was the conclusion from here?
We just wanted to know what is the symmetry of this M1, M2 and M3. Okay, so M1 is E symmetry, M2 is asymmetry, M3 is E symmetry, which means M1 and M3 have the in-plane vibrations. On the contrary, M2 has out-of-plane vibrations. And these out-of-plane vibrations have more electron phonon coupling involved in that. That's the conclusion from this one.
So when you mentioned that two acoustic phonon come together and gives optical mode, means in your Raman signal, how do you know that? Like two phonon or three acoustic phonon? Do you have?
Okay, so interesting aspect is that there is a paper published in 1970 in Pramana by Bera and Mohanty. They have done the theory that for the first time they mentioned that this two phonon mode can come from the interaction of two acoustic mode. Now, my job is actually is to find out the evidence, okay, from, because Raman can show it here. We found out, then we went to Umeshda. Now, Umeshda is actually like telling that there may be strain or something, so he has to rule out all the possibility, and that is what we wanted to. Now, the problem here is that when I am saying that because it is coming at 160 centimeter inverse, okay, half of that is 80 centimeter inverse. Now, this is 80 centimeter inverse, this is 85 centimeter inverse, these are the two modes, these are the two vectors in the acoustic vibrations. But the problem is this I in both of them, these are imaginary modes, we can't say at this moment, okay, we need to find out these are real or not, that possibility we have to rule it out. That is the struggle going on for last 2 months, okay. But certainly if these two modes leads to that, that is a good conclusion. But your theory says that, okay, it is coming because of the interaction here.
So these acoustic phonon modes are not optically active?
Acoustics are acoustic, I mean like, yeah.
So what is the way then to find their energy experimentally?
All the, all the thermal measurement you should, because acoustic vibrations carries the heat, yes. Brillouin scattering, of course, neutron diffraction is another one.
So do we know in these materials energy?
Energy of?
Acoustic phonon.
Okay. I mean like you do the calculation, experimentally people have done it neutron scattering. Neutron scattering people have done it, yeah.
Do we find something around?
See, neutron scattering or the Brillouin scattering, you go beyond Q equals to 0. Our struggle is Q equals to 0. We can't go beyond that.
So do we find something around 80? Sorry for pushing you.
No. Problem is the experimental requirement of the neutron scattering. They need 5 centimeter long sample, 5 centimeter minimum diameter, and I am sorry, that is not a single crystal for me, at least in these samples. And we have done a measurement which is like 1 micron spot size, total lateral dimension may be 10 micron or something, okay. It's just the thickness is varying, yeah. And
just for curiosity, this scenario disolate, did you do your measurement below superconducting transistor like this?
we did it, but I don't have the data, I have not.
I'm not sure that this mode will survive once it goes to a superconducting state. See, the reason why I'm saying is that earlier we did Raman to measure the band gap of superconducting. You must have known the classic experiment done in 70s. So there was a coupling of the phonon modes to the superconducting electron. So I'm just wondering, other ones anyway they are not superconducting also. This one if you take it down to 5K, just watch whether you get the 2 also.
I'll dig out the origin file, I think she might have done with the 3 Kelvin as well, so, so one of the,
just look for it.
I'll get back to you, I mean like, yeah.
There would be some influence.
So you can cool your sample down to 2K.
3 Kelvin, 3 Kelvin, yeah. Montana.
And there's no self-heating, I mean not self-heating but laser heating.
Laser heating also, you before taking the spectra you do power dependence at low temperature and high temperature. So because you know that
That's a serious issue.
yes, yeah. At low temperature it is an extremely serious issue because at room temperature the laser power maybe 10% is. See, another problem with that the samples also like poor thermal conductor, yes, because of the van der Waals gap. So anything you locally heat it can take out the tellurium out actually,
Yeah.
selenium or sulfur out, and it happened to GDT3. So we heat it up 200 degrees centigrade. So you see just tellurium, that's all. People do ion implantation and check the charge density wave. Okay, I don't know, like right now how we can do it here.
Disorder affects the CGW more than superconductivity.
Yes.
In fact, if you put more disorder, reduce the CDW, QTC can enhance. Because they are separate entities, they are fighting for the same Fermi surface. So if you try to reduce one, the other would pick up. So the disorder influence on CDW is more than disorder.
We need a very systematic disorder actually, not random disorder. That's a problem. And
Also, you need to do a nice measure of disorder.
yes. And I don't know whether I am looking for an answer whether magnetism affect the CDW or not.
Not on these lines. Not on these. But there are systems. Maybe we will discuss that.
Okay. Because in CDW equation you don't have any term associated with magnetism, so you don't expect it here. But we have a spin phonon coupling coming up. I don't know from where.
Talking about iron superconductor.
Yeah, iron arsenide.
Right.
Yeah.
Any more questions? If not, then let us thank the speaker again for this.
Thank you very much, all of you, for coming. Yeah.
Any is now left for you?
Well, that is also there. Thank you very much.